There seems to be some issues with sharing the screen. It's not allowing me to share from my side. So I'm going to hope that this works, that I can just do it from the website URL. And then I may not be able to spend as much time on each slide as I want, because if I wait too long, it seems to stop the sharing. So I apologize if this goes a little bit fast at times, but the slides are all online. So what I want to do today is talk a little bit about the theory of low-lying zeros, talk a little bit about some of the questions we look at, some of the tools and techniques we use. So the first question is, why do we care about zeros of L functions? So there's a variety of problems one can look at, from the infinitude of primes to the biases in certain congruence classes, to the Birch-Swinnerton die conjecture for zeros of elliptic curve L functions, to the class number. And it turns out that these problems, this is not, it keeps resetting. It turns out that these problems are related to properties of zeros of L functions. So if you want to prove formulas for the main term of the number of primes or primes in arithmetic progression, you just need to know that there are no zeros on the line real part of S equals 1. If you want better estimates, then you need the Riemann hypothesis that talks about the distribution of zeros in the critical strip. If you want to talk about biases between primes congruent to 3 mod 4 and 1 mod 4, this is sadly not good. It does not seem. Is there any way maybe you could share the slides and I could just tell you when to advance?
But I don't have your slide.
They're on the web, but what I can do is I'm posting it in the chat right now.
Okay.
And so if you can share those, I'll just say advance because it's not letting me share from my side.
Sure.
Excellent. If you could make it full screen, or
Okay.
it's easy if you just download the PDF and then share the PDF.
Okay, sir. So just a second.
So while you're opening up the PDF, I'll just continue talking for a little bit. And so the more properties we know about zeros of L functions, the more we can say about a bunch of problems in number theory that we care about. And so the goal of today's talk is to describe, what do we know about the zeros of L functions, and how does this help us understand? So there's a variety of different statistics we can look at. And so one of the first statistics that was looked at was spacings between adjacent zeros of L functions. And so if all you care about is the spacings between adjacent zeros, if you go very high up on the critical line, the spacings between adjacent zeros get smaller and smaller and smaller on average. And so one L function provides you infinitely many zeros to look at, and it gives you more than enough to look at. And so you can actually get limiting behavior in this case. So for the people who are joining, there's some issues displaying the slides. So we're just trying to get it to full screen right now. It's not allowing me to share from my device. So if you look at statistics such as the pair correlations or the spacings between adjacent zeros, you see a universal behavior for all L functions very high up. Excellent. So we're almost there. And these turn out to have the same behavior as a lot of problems in random matrix theory. Can you make it full screen now? Excellent. So next slide. Next slide. Okay, and so today, this is fun. So what I want to do today is just show you that a lot of these questions can be boiled down to trying to figure out what is the correct scale to study and what is the correct statistic to look at for a variety of problems relating to zeros of L functions. We'll see very similar behavior in many different systems. I'll discuss a little bit the tools and techniques needed to prove these results. So the techniques in random matrix theory, which does a great job of modeling, are very different than the tools needed in number theory. And unfortunately, on the number theory side, we don't have the same power. We don't have the same averaging formulas as we do in random matrix theory, which is why the results are not quite as strong. I want to go through the details for Dirichlet L functions, because in that case, you can actually get a good feel for how these calculations are done without having to be overwhelmed with all the technicalities and all the bounding lemmas and all the averaging formulas. And then I'll talk a little bit about cusp forms at the end and talk about how some of the work I've done recently with students has led to new world records for bounding how often L functions vanish to a given order at the central point. Next. And so the general formulation is we have some system and we observe values, say T1, T2, T3, and we want to understand what rules govern the spacings between the events. So there's lots of different situations you can be looking at. You can be looking at energy levels of heavy nuclei, eigenvalues of matrices, primes, zeros of L functions. Next. And so there are three key steps in the analysis. The first is to determine the correct scale to study the events. And usually this is pretty straightforward, often follows from a central limit theorem. The next is to develop an explicit formula relating what we want to study to something we can understand. And our motivating driver for this will be the eigenvalue trace lemma from the algebra. And then the last, which is the most difficult, is developing an averaging formula so that we can actually analyze the quantities that emerge. So unfortunately, it is not always easy to figure out what is the correct statistic to study. And that's often a challenge, trying to find something that will be combinatorially tractable. Next. Next. So I'm going to talk a little bit about classical random matrix theory. So the three-body problem, 3-point masses and general configuration, is intractable. We can't write down a closed form solution. So if we can't even solve this problem, imagine how much worse it's going to be with something like heavy nuclei like uranium. We have over 200 protons and neutrons with a far more complicated force of interaction than gravity. So the main idea that physicists came up with was you can get some information about the structure of the nucleus by shooting a high energy neutron in and seeing what happens. And we'll see that there's an analog of this in number theory. And so the energy levels of the nuclei will correspond to the zeros of our L function. And then the energy of the neutron that we shoot in is going to be replaced by a Schwartz test function. And the energy level of the neutron will become the Fourier transform of the Schwartz test function. And on the physics side, we'd love to shoot an arbitrarily energied neutron, but we can't. On the number theory side, we'd love to use a test function with arbitrary support, but we can't. And so we need to try to see, based on what we can shoot in, what can we deduce afterwards? So the fundamental equation from quantum mechanics is you have your Hamiltonian and you have your energy eigenlevels En and your energy eigenstates Cn. The problem is two things prevent this from being a standard linear algebra problem. The first is H is infinite by infinite. And the second is we don't know any of the entries. So, trying to diagonalize an infinite by infinite matrix where you know no entries is of course a challenging problem. Next slide. So Wigner's great insight was to use some motivation from statistical mechanics. And what he basically said is, if we can't write down the matrix, what if we just consider a whole ensemble, a large collection of similar matrices? And we'll average over each one of them. And for each one of them, we'll compute. And the hope is that most matrices' behavior will be close to the system average. And then frequently some physical symmetries, some physical properties of the system we're looking at will surface in the types of matrices we look at. And so, depending on your physics laws, you might force your matrices to be maybe real symmetric or complex Hermitian. Next. And so just a little bit more explicitly, let's say we have a real symmetric matrix. So A equals A transpose, Aij equals Aji, and then the probability of the matrix is just going to be the product of the probabilities of the independent entries. So that's the main diagonal and everything above. Or even more explicitly, the probability we have a matrix where the element Aij is in an interval alpha ij, beta ij, would just be the product of integrating the probabilities in those range. And we want to understand the eigenvalues. Thank you. No, you did it perfectly. You anticipated me perfectly. By all means, keep anticipating me. So let's let delta be the Dirac delta function. So this is a unit point mass at x naught. So that means if we integrate f against delta of x minus x naught, it just returns f of x naught. Next. So to each a, we can associate a probability measure by putting a mass of 1 over n, because there's n eigenvalues, and we're going to normalize the eigenvalues by 2 square roots of n. And so if we want to count how many eigenvalues or how many normalized eigenvalues are in the interval a, b, we just integrate from a to b, and that just gives us a really nice count. Next. And one way to understand this function, this density, is to calculate its moment. So the kth moment would be just integrating x to the k times the density. Well, x to the k is going to be a normalized eigenvalue divided by 2 root n to the kth power. And we'll talk a little bit more about this later, but the sum of the eigenvalues to the kth power is just the trace of a to the k. And so we actually have a hope of understanding this, and then we just multiply this by the probability we chose the matrix A, and then we integrate over all such matrices. Next. And so this is not the most general case, but it gives a flavor of the type of results. So Wigner proved that if you consider the set of n by n real symmetric matrices with the entries independent, identically distributed random variables with mean 0, variance 1, finite moments, then as n goes to infinity, for almost all A, the density of eigenvalues converges to a semicircle. Next. And again, I remarked briefly as to what's allowing these calculations to work. It's the eigenvalue trace lemma, that the trace of a to the k is the sum of the eigenvalues to the k, or explicitly, if you expand out trace of a to the k, you get a polynomial in the matrix elements. So why is this so wonderful? Well, we want to understand the eigenvalues of our matrix, but it's the matrix elements we choose. So this allows us to convert from understanding the matrix elements, which we know, to understanding the eigenvalues, which is what we want. And the idea is, since the sums of the kth powers of these other moments, a good probability distribution is determined by its moments. So this shows that there should be a hope of this calculation working. So again, this is an extremely rich subject. This is just a fast introduction of the motivation from random matrix theory. So if you go to the next slide, we now turn our, oh, sorry. Yep. So this is the last thing I want to say about random matrix theory is just trying to figure out what is the correct scale. And so if you look at the trace of a squared, it's the sum of the eigenvalues squared. So by the central limit theorem, the trace of a squared is the sum of aij, aji. Each one of these has mean 0, variance 1. So each one of these is roughly of size 1. We have n squared of them. That gives you an n squared. So if the sum of the squares of the eigenvalues is of size n squared and there's n of them, that means each eigenvalue on average is of size square root of n. And this is why we were dividing by 2 root n. It's the root n that's important that gives us the correct scale. The 2 is just telling us, let's be fancy, let's say semicircle rather than semi-ellipse. Next. And then, to just, do the calculations in greater detail, we now put that in, we multiply by the probability of the matrix, and then we just have to integrate these polynomials. Doing this involves some combinatorics, expanding things out, things factor, and then depending on the structure of your matrix, these calculations can become quite complicated, but there is a real chance of being able to do them. Next. And so in the case of the real symmetric matrices, after doing some combinatorics, you see the Catalan numbers emerging, which interestingly do occur in many problems of L functions. All right, next slide. So what I want to do is just briefly make sure we're all on the same page. Next slide, and just quickly introduce L functions. So hopefully everybody has seen the Riemann zeta function. It's defined as the sum of 1 over n to the s if the real part of s is greater than 1. And by the fundamental theorem of arithmetic, this is the same as the product over primes of 1 minus 1 over p to the s inverse. It has a functional equation relating its values to s to 1 minus s. And we believe it satisfies the Riemann hypothesis that all the non-trivial zeros, all the zeros in the critical strip, real part of s between 0 and 1, have real part 1/2. That means we can write them as 1/2 plus I gamma, which means we can order the zeros. And you now see the analogy with nuclear physics. Here we have the different energy levels. You can view the gammas as the different energy levels of the zeros. And the observation is that the spacings between zeros seem to be the same as the spacings between eigenvalues of complex Hermitian matrices. Next. Of course, rather than looking at just the Riemann zeta function, we could look more generally at a L function. And for us, an L function is always going to have an Euler product. So I'll have some sum of AF of n over n to the s is some product of factors that only depend on the prime. It will have some functional equation. And again, we believe that all the zeros have real part 1/2 in the critical strip. And that's now the generalized Riemann hypothesis. Next. And so as an example of just how good the agreement is between the two subjects, here is some numerics from Andrew Odlyzko looking at 70 million spacings between adjacent zeros of zeta, starting at the 10 to the 20th zero. And you see phenomenal agreement with what he observed for zeta and what you observe when you look at the eigenvalues of the Gaussian unitary ensemble. So next slide. So let me give you a sense of how the random matrix theory arguments generalize. So the first is trying to generalize the eigenvalue trace lemma, which related the eigenvalues which we wanted to the matrix elements. So in complex analysis, whenever you see a function, you should have a Pavlovian response to take the logarithmic derivative and do some type of contour. We get a lot of information from that in terms of zeros and poles, and you can even do a little bit better if you hit it with a test function, which we will in a moment. So we take the logarithmic derivative of zeta, and so we look at zeta prime of zeta, and we have two different ways of writing it, but we're going to use the product because the logarithmic derivative, the log of a product is the sum of the logs. And so we then take the derivative term by term, and then we use the geometric series formula to expand the bottom, and we get log p over p to the s plus something good. And so this shows us that if we now do a contour integral of zeta prime over zeta, there's a hope of being able to say something about this. Next. And so we hit it classically to prove the prime number theorem with x to the s over s. And then on the right-hand side, if p is less than x, the integral is going to be 1. If p is greater than x, the integral is going to be 0. And this just gives you the sum of log p, and that's going to be related to the pole and then sums over zeros. Next. Instead of x to the s over s, we could take some test function phi, and then the only change on the right-hand side is now we have phi to the s times p to the negative s. Next. Well, we can write p as basically e to the negative s log p, and you can see that what we have now looks like a Fourier transform of phi times something. There's the e to the it log p, so it looks like a Fourier transform of a function related to phi evaluated at the log of the primes. And so we have a formula that's now going to connect sums over zeros from the left-hand side when we do the contour integral to sums of phi hat over primes. Next. So if you do the calculations explicitly for the Riemann zeta function, this is the explicit formula you get. And again, this is the analog of the eigenvalue trace lemma. And the idea is we have parts of it that are just straightforward and don't depend on anything about primes, the gamma factor stuff. And then we have some sums over primes of our test function. All right, next slide. You could also do this for Dirichlet L functions where chi n is a character, and you get the following formula. And if you look, I've expanded things out so we have for the sums, we have the sums over primes, prime squareds, and all the prime cubes and higher terms, they turn out to give you a lower order term, so we can just throw them away. It's just going to give you a 1 over log m. And this is just coming from looking at the explicit formula, looking at the geometric series expansion, just being a little bit careful. This is the analog of the eigenvalue trace lemma, that we now have these sums over zeros as related to sums over primes with the coefficients of our L function. Next. And so another example that we're going to look at later is what happens if we look at cuspidal new forms. Again, you get something a little bit different, but again, the explicit formula gives you that these sums over zeros is going to be equal to sums over primes times the coefficients of your L functions, and that's the pf phi at the bottom is the sum of lambda f of p times the Fourier transform of our test function at log p over log r. And so if we can understand these sums over primes, we can deduce things about the zeros. Next. And so the first statistic that's looked at is the N-level correlations. It's talking about how many times, if you look at tuples, do the differences lie in a box? In the interest of time, I'm not going to say too much about this. This is the work of Montgomery. Next. And a couple of results is that we were able to prove by work of Montgomery, Hedgel, and Katz-Sarnak that the N-level correlations of L functions for suitable restrictions agree with those of random matrix theory, of the Gaussian unitary ensemble. And so for a while, people thought you only really need to understand one type of matrix to understand zeros of L functions. But remember that all of these statistics are insensitive to finitely many zeros. I can throw away finitely many, and it's not going to change the limiting behavior for spacings between zeros. And so a new statistic was studied that depends only on what's going on near the central point. And the advantage of that is that when we look at what's going on near the central point, there's often things of arithmetic interest. So if you're looking at families of elliptic curves, well, the order vanishing at the central point by the Birch-Swinnerton-Dyer conjecture is the rank of the Mordell-Weil group. And so that there should be tremendous information in what's going on there. And now we're in a situation where finitely many zeros will matter. In fact, that's the entire story. So the statistics of N-level correlations and spacings between zeros is not strong enough to answer questions like Birch-Swinnerton-Dyer. And so we need a new statistic. Next. And so the new statistic is the N-level density. And so what we do is we take Schwartz functions. And so we'll just assume that our Schwartz function phi can be written as a product of Schwartz functions, one in each component. And then what we do is we evaluate our test function at scaled zeros. Now, the scaling is dependent on the analytic conductor, which comes from the functional equation. The whole point of this is to adjust things so that near the central point, these normalized zeros have mean spacing 1. And this is just going back to the first point I mentioned of trying to find the correct scale. Now, because phi is a Schwartz test function, we've now scaled these normalized zeros to have mean spacing 1. The further you go away, the less contribution you have. And so almost all the contribution is going to come from the zeros near the central point. Next. And so, again, just summarizing, so individual zeros now contribute. Most of the contributions from the zero at the central point or the ones very close to it. And unfortunately, unlike the statistics we looked at before, where one L function had infinitely many zeros to look at, we only have a couple of zeros for each L function that really contribute. So we have no chance of getting a nice average quantity for just one L function. What we need to do is we need to average over several L functions. And so we average over things in a family. And so, for instance, a family could be Dirichlet L functions. It could be cuspidal new forms. It could be elliptic curves. There's lots of different families you can look at. And the Katz-Sarnak conjecture is if I give you a nice family of L functions, like one of the ones I just mentioned, then in the limit as the conductors go to infinity, and you should think of the conductor as the analog of the size of the matrix, then the N-level density converges to something that depends only on the symmetry group and agrees with a subset of unitary matrices. So either unitary matrices, symplectic matrices, or a type of orthogonal matrices. Next. So you have to figure out, technically, do I want to look at the local renormalization where I use the analytic conductor of the L function, or global, which is a little bit easier, using the average log conductor. If you're only looking at one level densities, it doesn't really matter. But as you start to look at two levels, there are some issues, and it turns out it's best to just use the local and deal with some of the complications. Now, if you're lucky and you're looking at families of cuspidal new forms or Dirichlet L functions, all the conductors are the same for a given level, and so this problem doesn't appear. And so again, explicitly, the idea is the N-level density should converge to integrating a test function against some density function W that depends only on the symmetry group. Next. And so just explicitly recording what the different symmetries are. Here, delta naught is the delta function, Eta is 1 if absolute value of u is less than 1, 0 if it's greater than 1. You can see that unitary and symplectic are different from the orthogonals, but if your test function is supported between -1 and 1, you actually can't distinguish the three orthogonal flavors. And you could be in a ridiculous situation where all the terms, all the forms in your family have even sign, but the underlying symmetry is SO odd, not SO even. So what this tells us is we really want to understand large support. The larger support we have of the test function, the more we can say. However, there's another approach you can take, and you could look at the two-level density. And if you look at the two-level density, it turns out arbitrarily small support is enough to distinguish the different flavors. Next. And so I had mentioned this a little bit earlier, but it's really worth driving this home because this is the motivating philosophy as to what we're doing. The zeros of L functions correspond to the energy levels of heavy nuclei. The Schwartz test function that we shoot in and evaluate the zeros at corresponds to the neutron we use in physics. And then the support of the test function, where we can actually evaluate the sums over primes, corresponds to the energy of the neutron, where we can do the calculations. Next. And so there's a lot of different results in number theory. In the interest of time, I'm not going to state them all, I'll just leave them here. But we've now shown that many families, for suitable restriction, the number theory and the random matrix theory agree. Next. And again, similar to random matrix theory, there's three key steps. The first is controlling the conductors. It turns out in my thesis, I was able to show if you can deal with families where the conductors are monotone increasing, that's usually enough. Fortunately, most of the families we look at, the conductors are constant, so it's not really a problem. We need some kind of explicit formula, which relates the sums over zeros to sums over primes. So this is essentially the explicit formula of Riemann. You're going all the way back to proving the prime number theorem, and we just have a generalization of this to other L functions. And then the most difficult part is the averaging formula. If we don't have a good averaging formula, it doesn't help us that we can relate the sums over zeros to these sums over primes times the coefficients of the L function. And that's the difficulty for L functions right now, is we typically don't have great averaging formulas. Next. And so why do we care about statistics like this? Well, one of the reasons, and I'm going to talk about this in more detail later, is that we can use this to bound the order of vanishing at the central point. So if we take phi to be an even Schwartz function that's non-negative, then if I throw away the contribution from all the zeros except the zero at the central point, I only make the sum over zeros smaller. And so you would get the average rank times phi of 0 is thus equal to the integral of phi times our density. And so if you use the higher level densities, you can get even better results. And a couple of years ago, Chris Hughes and I proved that you can use this to show that the decay of, you can get a decay in the bounding of order vanishing. What's the probability you vanish to order at least r? And you can get it some constant Cn times r to the negative n. Now, what is great about this is the larger n is, the greater decay you have as you go higher and higher above the central point. I mean, higher and higher rank. The problem is that constant Cn also grows. And you could have the unfortunate situation where, for small, rank, you would get a bound that at most 250% of the forms vanish to that rank. Well, we don't really need to do a lot of work to prove at most 250% of the time something happens. So these results are much better the larger n you use, the further you increase r, the more zeros you try to say, well, what if I had 10 zeros or 12 zeros? How likely is that to happen? So as you increase the number of zeros at the central point that you want to bound, how often that happens, these results become better and better and better. But it's possible for very small values of r that as you use larger values of n, you get a worse result. Okay, and we will talk a little bit later today about doing everything carefully and just seeing how good of a result can we get by using these higher level densities. So Katz-Sarnak only looked at the one level, we're going to look at higher levels. So now turning to the next step, we're going to look at Dirichlet L functions. Next slide. And I'm going to just go through this example in a little bit of detail to give you a flavor of how you do the calculations, and then we'll turn to cuspal new forms and talk about some recent results. So next slide. So just to put everybody on the same page, we're going to look at M as a prime. We have the cyclic group Z mod MZ star. We can explicitly write down what the principal character is. We know that there's M minus 2 such characters, and we can explicitly write down what they do to a general group element in terms of what they do to a generator. And again, the whole point of this is to just show you that all these calculations can be made explicit. There's no need to follow all of this carefully right now. The idea is just using a classic result from elementary number theory and algebra. We can write down everything explicitly. Next. And so using this, we have the Gauss sum. It's going to be a modulus square root of M. We can write down the L function. We can write down the completed L function. And again, everything is just explicit. Next slide. We now use the explicit formula, which relates the sums over zeros to sums over primes. And when we do this, it turns out, again, that the only ones that matter is the sums over primes and prime squareds. All the other stuff gives you lower order terms. So we just have to understand these weighted sums of the Fourier transform of our test function at log p times chi of p or chi squared of p. And of course, by symmetry, the chi bar is going to give you very much the same thing. All right, next slide. So we need to evaluate, as I said, these sums. What's nice is because the conductors are constant, we notice that the Fourier transform phi hat is always evaluated for fixed prime at the same thing. So I can pass the sum of the characters through the sum over the primes and go straight to the characters because phi hat is independent of the character. If the conductor is dependent on the character, this wouldn't be the case and it would be a lot more work. This is one of the reasons why I like this example so much. It really highlights what's going on. Next slide. And so now we just have the standard orthogonality relations, the sum over the characters, we know what it is. Well, if the prime is not equal to M, which is the conductor, we have the following. And so when we substitute that in, we get really nice formulas for that. So next slide. So just putting everything in, we get bounds like this. Next slide. And then just trivial estimation, keep going. And then at the end of the day, you see, oops, go back one. You see that you get a bound of M to the sigma over 2 divided by M. So as long as the support, phi hat is supported between minus sigma, sigma, as long as sigma is less than 2, it turns out this term doesn't contribute. If you want to go beyond 2, it turns out you need to know more results about how the primes are distributed in arithmetic progressions, in particular, how the primes are distributed mod, how often they're equal to 1 mod M. But getting up to support minus 2, 2, is extremely elementary. Next slide. Then we have to do a similar thing for the sums of chi squared. And again, we use our orthogonality relationships. We tweak things a little bit. And again, it's very similar algebra. Next slide. And so I want to now quickly turn to cuspal new forms. And so Vanishing and Sarnak proved that the one level density agrees with that of SO even or SO odd if you split by sign in the region all the way up to minus 2, 2, which was quite impressive to go that far. And so Chris Hughes and I extended this to not just the one level, but to the n level density. Originally, Vanishing and Sarnak just did it for square free level. With some students, I removed that assumption. It becomes a technical monster. Next slide. And so this is just a quick review of what is a cuspal new form. We have some congruence group, A, B, C, D with C congruent to 0 mod n. We have forms, they transform nicely under these groups. They have a Fourier expansion. We have a Peterson norm that talks about the size of f dot g. And then we just normalize the coefficients. So there's several different ways to normalize the coefficients of L functions. I can always rescale an L function by a fixed constant and it's still going to satisfy the same functional equation. So normally you adjust things so that either the L2 norm is 1 or the first coefficient lambda f of 1 is 1. We'll do lambda f of 1 is 1. Next slide. And then the key result is the Peterson formula, which says if you look at the sum of the normalized coefficients and we sum over all f in a basis, then if m is equal to n, then we get this term of 1, that's the delta m and the Kronecker delta. And if not, we get this Bessel-Klustermann sum, which turns out to be a real pain to understand, but it can be done. And so the idea is this is the averaging formula we need that allows us to try to understand the sums of the Fourier coefficients. But again, it's only useful if we can then deal with this Bessel-Klustermann piece. Next. And so we have an explicit formula. This is the one I mentioned earlier that relates the sums over zeros to these sums over primes. And so now we just have to understand these prime sums. And then if we want to split by sign, it's going to tweak it a little bit. So this is just looking at a specific form. Next. And so, as I remarked, the Fourier coefficients have some remarkable properties. They're multiplicative. And it turns out that the sign of the functional equation, epsilon f, is basically a bunch of really nice numbers times lambda f of n, times the nth Fourier coefficient. So if I look at 1 plus or minus epsilon f, that's going to be equal to 2 if epsilon f, let's say I do 1 plus epsilon f. So if the sign is even, if the sign is 1, I get 2. If the sign is odd, I get 0. So if I multiply by a factor like this, I just double count all the even forms and I don't count all the odd forms. And the other way, of course, if I wanted to study just the odd forms. So the advantage of this is by multiplying like this, I can convert my sums to 2 new sums. One is just the same sum I had before, and the other is essentially multiplied by lambda f of n. And that's why I'm going to need to use the Peterson formula twice, once for just lambda f of p, and one for lambda f of p times lambda f of n. Next. And so then we just have some results from Bhubaneswar. We have the beautiful Ramanujan sum, which arises when we look at the Klustermann sum. And all I want you to get from the bottom is that they found a way to handle the sums that arise in closed form. And so our work is to try to reduce whatever we have to the same form that they have. Next. And so, just going through some of the details, if we want to get trivial results just by naive estimation, if the support is small, we can essentially just bound things by trivial bounds, put in absolute values. How large can the Klustermann sum be? How large can the Bessel function be? How large are the Fourier coefficients? And that gives us a pretty good answer. Next. If we want to go a little bit large, if we want to go to support up to 2, then it becomes a little bit harder. And then what we do is we follow Vanishing. We use Dirichlet characters to expand out the Klustermann sums. We end up getting functions involving the Bessel function times the test function. And Vanishing made this work up to -2, 2. Next. I'm just going to record some things for greater generality. I'm trying to just leave a couple things in the slide in case anybody's interested. I'm of course always happy to chat, and feel free to just shoot me an email. Next slide. And then we just start to get more involved sums coming into play. But these are sums involving standard functions from number theory. And so there's a hope of being able to handle them and then just estimate them. Next. What I want to show here, what I want to focus on is the one really clever idea that emerges when you try to study things involving the 2-level density. So we want to reduce everything to a Vanishing. And so unfortunately now we have a Bessel function involving 2 variables, and they had a Bessel function involving 1 variable. So if we let u2 be the product of x1, x2, and u1 be just x1, then when we calculate the Jacobian, it's 1 over u1. And when we put things in, we now get a Bessel function of just 1 variable, like the Vanishing, and we have our Schwartz test functions at the log of u1 and the log of u2 minus the u over u1. Next slide. Well, that's really integrating phi hat of w, phi hat of log u2 over log r minus w1, because the log of a quotient is the difference of the logs. This is just a convolution. So what we've really done by doing this change of variables is we introduce a new test function c2, which is phi convolved with phi. And when we substitute in, we now get essentially the exact same integral that Vanishing looked at. The difficulty is when we try to compare this to random matrix theory was expecting that we would have a double integral. We cheated and we converted it to a 1-dimensional integral. We have to pay the price by doing some painful combinatorics. It can be done, but nothing in life is free. It's worth paying the cost of doing the combinatorics to get out of having to deal with a Bessel-Klustermann piece involving 2 variables. Next. And again, if you wanted to, it's not a surprise as to how you would do it if you had the 3-level. you would just do the change of variable with the products again, and everything works out very nicely. Next. And so, this is just to record what the different things are. I think in the interest of time, I'm not really going to go through all the details of the expansions you get on the random matrix theory side. Next. And then just when you expand everything out, you just are able to show agreement. And now your test function is a convolution and everything becomes very nice. Next. And so if we do some careful bookkeeping, we can get support up to 1 over n minus 1. And so before the trivial stuff is up to 1 over n, we can get up to 1 over n minus 1. There's some obstructions that prevented us from getting all the way up to 2 over n. The question becomes just how far can you push this? And so this past summer, I had some students who were doing a monumental amount of work to try to push this further to 1 over n minus 2, 1 over n minus 3, 1 over n minus 4. And most of the terms can be handled without too much trouble. Some terms can be handled with a great deal of trouble. And there's 1 or 2 terms that we're still just trying to finish, but we're guardedly optimistic. And what's nice about this is that the larger support we have, the better results we can get on vanishing. So one way to get better results on vanishing is to look at higher level densities. Another is to increase the support. But it becomes harder and harder and harder to make the support larger and larger and larger. Next slide. And so just showing a little bit of the various things that come into play, to just give you a little bit of a flavor of the partial summation that comes up in the forms we need to deal with. Next slide. And then just you keep breaking things up into different cases. You have to do a lot of inclusion exclusion. You have to worry about how often is this prime the same as that prime. Next slide. And so what we've shown up till now is we've provided more support for the random matrix theory conjectures, the Katz-Sarnak, that the zeros near the central point look like the eigenvalues of a family of unitary matrices, either unitary, symplectic, or orthogonal. We have control of conductors, we have averaging formulas, and we can use these to get some order vanishing estimates. So if you go to the next slide, what I want to end with today is just talking about the recent work with a variety of my students on trying to increase the support and trying to get better bounds on how often do you vanish to rank R or higher. So next slide. So what we want to do is we want to show, assuming GRH, that we can get support up to 1 over n minus a. And again, my students were getting very close to getting all the way up to 1 over n minus 4, but there's still a couple of terms left that we have to do. And of course, if there's even one term that you can't do, then you have a fundamental obstruction. We have reason to believe that most of the terms can be handled without too much trouble. But again, if even one term is resistant, then we no longer are able to push it this far. And so sometimes, rather than computing the n-level densities, we compute something that's very similar, the nth-centered moments. And again, this is very similar to probability theory in terms of just, if you understand the centered moments, you should understand the distribution. Various things just turn out to be better combinatorially. And so the calculation is going to be very similar. The square brackets means, I average over the family. So next slide. And so when we expand out, the sum S2 that we have to deal with, we get a lot of terms. And then as we increase the support, we get more and more terms that emerge. What's really going on is we have an indicator function of the sum of the x1 through xn. And if the sum of x1 through xn is between -1 and 1, nothing, it's a 0. But if it exceeds -1 and 1, it could contribute. And so if the support of everything is at most 1 over n, then if each xi is at most 1 over n and I sum n of them, I'm always going to be between -1 and 1. But now assume that the sum of the xi's has to be between -1 and 1. And now I could go all the way up to 1 over n minus 1. Well, if I can go up to 1 over n minus 1, if everything is of the same sign, I could actually go too far because I could have n divided by n minus 1. But if one item is negative and everything else is positive, then the largest the positive sum could be would be n minus 1 times 1 over n minus 1. And then the negative thing would keep us within the interval -1, 1. So we see that if we try to go all the way up to 1 over n minus 1, we're okay as long as there are two terms of different sign. But if everything is of the same sign, it could be pushed beyond minus 1, 1. If we try to go up to 1 over n minus 2, we would need at least 2 terms negative and everything else positive, or 2 terms positive and everything else negative. And so you start to see that there's more and more things that can contribute, and that's what makes things so challenging. Next slide. And so this is just a little outline as to what we're doing. We expand our sum into various subterms. We imply inclusion, exclusion. We expand the Fourier coefficients, the Bessel-Klustermann terms. We expand the exponential sums using Dirichlet characters, similar to what Bhubaneswar did. Then we use Millen transforms to convert these integrals, and then just pray that we can do the number theory. Next slide. And so what we've done is we've extended and generalized to these centered moments, which is essentially the same as the n-level densities. And what we want to do now is we want to have the maximum freedom. So the more different choices of test functions we have, the better results we can get. And so the original paper that I did with Chris Hughes, we assumed all the test functions were the same. So with one of my students, we actually figured out how to generalize to allowing phi1, phi2, phi-n to be different. The key ingredient was we needed to come up with a new ancillary test function that we could use to pointwise bound things. And then the next few slides, if you go forward, is just going to be a result of what we've just seen. So this conference is supposed to be about recent results in number theory. We are getting close to being able to put this paper on the archive. We're just finishing things up right now. And here is recording the results we get for vanishing of order 6, 8, or 10. And for each of these, it's vanishing to order at least 6, order at least 8, at least 10. If you use the 1-level density, you get your bound of 0.14, the 2-level 0.015, and the 4-level 0.0085. For the 8 and the 10th, you can see it's even better. And so the point of this is to just show you how powerful these results are, that the larger support that we can get, coupled with the higher moments, gives us better and better estimates for how often we have order vanishing to a given level or higher. If you go to the next slide, this is similar results for odd. For 5, the result is really not that much better. You're going from the 2-level bound of 0.067 to the 4th bound of 0.0658. Again, a very small improvement. And that's typical of a lot of results in fields like this, that the initial papers have remarkable improvement, but then the subsequent papers, you're just changing deeper decimals. But when we start to get to order vanishing of at least 7 or 9, you can see now that there is significant improvement in the bounds. We believe for these families that half the forms in the limit should be ranked 0, half the forms should be ranked 1. So we expect all of these bounds to be 0, and we're starting to see things a lot closer to that using these new methods. Next slide. And then again, if you go to much, much higher vanishing, say order 500 or higher, 600 or higher, and so on, we see the bounds for the 1 level is still a respectable 0.0017. The 2 levels of size 10 to the negative 6, and then 4-level bounds of size 10 to the negative 12. And so we can see that significant improvement in using these higher ones. Last slide. And so again, not surprisingly, you see something very similar if you look at the odds. Next slide, in case there's something new. This might be the last slide. Okay, so just to quickly recap, the theory of Katz and Sarnak say that the zeros near the central point are well modeled by the eigenvalues near 1 of a classical compact group. We need to understand 3 things: how to control the conductors, how to find the correct scale, and some kind of averaging formula, some kind of explicit formula that relates what we want to study to something we can study, and then an averaging formula to allow us to do that. In random matrix theory, it's the eigenvalue trace lemma. In what we're doing here, it is the explicit formula from Riemann. And then we just need to execute these sums over primes. And that's where the number theory comes in. It's often quite challenging. We don't have as good results here as we do in random matrix theory. because in random matrix theory, you're integrating polynomials against the probability of a matrix. These are actually integrals that are not too bad to do. The number theory ones are tremendously harder. We've been able to make some progress in understanding the behavior of zeros near the central point. These are called the low-lying zeros for a lot of families of L functions. And what we're able to do is we're able to show that we do have agreement with different classical compact groups. We can identify which one. And if we choose our test functions to be even, Schwartz, non-negative, we can use these to get bounds for vanishing to order R or higher at the central point. And by looking at the higher level densities, rather than just looking at the one level density, the combinatorics and the analysis becomes much harder, but the dividends are tremendous. We can see remarkable decreases in the probabilities of vanishing to order R or higher. And so again, the two ways to get better results here are to look at the higher level densities or to increase the support of the test functions where you can do things, or even better, to do both simultaneously. So thank you again for the opportunity to come and speak to you. If anybody has any questions, I'm happy to chat briefly before I run to catch my bus. And then feel free to shoot me an email. I will put my address in the chat right now. So thank you.
I'd like to take this opportunity to express my deep regards to our keynote speaker, Professor Miller, sir, for such a wonderful and informative talk on evidence for the Katz-Sarnak density conjecture for low-lying zeros and application to central point vanishing of L functions. Thank you so much, sir.
Thank you. Have a great day.
We have some questions from the participants.
Sir,
I would like to address those questions.
No. Participant can send to the Professor Miller's mail address. Actually, he is outside. Am I right, sir?
Yes, I just put my email in the chat. So if anybody has a quick question, I know we have another talk very shortly. I apologize. We had some technical difficulties in sharing the screen. So if anybody has a quick question, I'm happy to answer it. If not, I put my email in the chat.
Stephen, I have a question.
Yes.
Are you able to hear me?
Yes.
Yeah. So do you also look at the gaps between zeros?
So I have not looked at the gaps near the zeros. You could try to do that near the central point. People have looked at the gaps between zeros far up on the critical line. And when you do it far up on the critical line, this is the Montgomery or Bliscoe law, which has been known since the 70s, at least conjecturally. But
Right.
again, you can do that because you have infinitely many zeros to look at. Near the central point, we only have finitely many.
So yeah, I mean, your predictions, they show any evidence of pair correlation, conjecture? That's what my question
was.
Well,
so the pair correlation is a very different statistic. So the pair correlation, you need to have essentially infinitely many zeros to look at, because you can throw away finitely many zeros and it's not going to make any impact on the pair correlation. Since we're looking at what's going on near the central point, going on near the central point is a very different beast. Yeah. And this is because of interest in questions such as Birch, Swinnerton, and Dyer.
Right. Okay, thank you, Steve.
Yep, you're welcome.
Yeah. Bye.
So let's thank you again, Professor Miller, for being with us and spending his precious time from his busy schedule. We are really honored to have you, sir.
My pleasure. It was great to be here. Hopefully next time in person. I'm sad to miss the next talk, but I'm glad it is being recorded. I have to go run and catch a bus now. Have a good day, all.
Thank you, sir. Now I request Dr. Patel to continue the session.
So I take this opportunity to welcome our resource person, Professor K. Srinivas. So I think Sir is present, and I request Sir to sit in.
Yeah, let me share the screen.
Yes, sir, please.
You may have to make me as a host.
Yes, sir, I have already made you.
I have two accounts, okay, K. Srinivas and Srinivas Kuttedia.
Sir, so which account? K. Srinivas, sir? Okay, so
One second.
just
No, Srinivas Kotyada, you can make it. Okay.
okay. Sir.
Why I'm not able to share? Why I'm not able to share?
I don't know, sir, but it